Hello, it's Jason Greenwood here. Just checking in. It looks like we have attendees still connecting at this point. This is the AMA webinar, Advanced Geosciences. The format is such that the questions can roll in at any time. I've received a few already. There's really a mix of topics here. I've got just the first page, a few slides just to introduce what we'll be going over. This is all focused on resistivity IAP, electrical resistivity tomography. And bear with me here just for these first few slides. This is directly coupled transmitter receiver. This is a 4-electrode pair, just showing you the basics of the measurement. A couple of the first questions will relate to this actual pseudo plot point. And that's the potential field we're creating, and sampling. That's actually a Wenner array, but just showing you the current lines and equipotential surface. Again, this is directly coupled resistivity IP, and it's an Ask Me Anything webinar focused on these methods, primarily on processing. And then this is the dipole-dipole array, directly coupled with electrode stakes. And this is the passive resistivity cable, and that's a nice point source there. That's the cleanest way to collect these data. I'm going to go ahead and look at this first question. Now, you do have a an interface there for asking questions, and it's a chat interface. So feel free to connect that way, and I'll announce those questions because you won't see the answer in text. It'll be a part of the AMA at that point. Okay. First question is just a little bit of field issue, I would say. When you're collecting 2D lines with the SuperSting, there can be one command file for any measurement settings and any electrode spacing which your cable is capable of doing. So let's say you have 56 electrodes with a maximum of 6 meter spacing, or about 20 feet. And your particular project needs to deploy at 2 meters. And so when you set up that file, you load your 56 electrode dipole-dipole command file. And in the field, there's a question called scaling factor. And only the operators in the field know what they physically place that cable at. And let me show you, just going back here, what I mean by that. See, that's a 3D array. Let's go to the next one. Here's a 2D array. And if that was installed at 2 meters, but they put a scaling factor of 3, the line would show up too long, and the actual resistivity solved for in the modeling would be incorrect. You may have fitting issues. So there is, with 2D, it is possible to rescale it. Now, in 3D, that's not the case because it's much more complex. You have issues where certain dipole combinations should not be collected if they're beyond a certain distance. So with 3D, you don't use scaling at all. So that's a whole nother set of questions. But for 2D, we can fix these scaling issues. Let me show you how to do that. So here is the line, and from talking to the end user, they told me that they entered a 3 for the scaling factor. This is on the supersting in the field, but they deployed at 2 meters. So when we load this in Earth Imager 2D, it's always important to default to surface. We'll go into that later. I'm going to load these data. Now this is the original file, and this does have some. This is a roll along, and they do have some noise, and I believe they have some cable issues. There's a this may be a third-party cable, but that is apparent in the raw data. But beyond that, if we were to solve this model right away, they would see, or to look at the total length, it's incorrect. So we'll just let this solve. It's going to tell us the electrode spacing there, 3 meters. And the project manager knows right away that that's incorrect. So beyond filtering it, you can see this 81% misfit. If I right click here, we look at the cross plot, there's a lot of scatter. So this is very noisy data for a number of reasons. But the first order of business is to rescale it. There's a function there, transform electrode coordinates under tools. And this is Earth Imager 2D. So go here, and there's a scale distance. I'll read in that original file. There we go. And it's going to be renamed automatically scaled. And what I've done is taken the correct value and the value used in the field, and so that's 2 divided by 3, and I get this number here. So I'm actually going to just copy that out just to use the full accuracy, and then hit scale and save. So that's that scaled number. Load that one. And this is a long line, but now it's the correct length. So you see electrode spacing is 2 meters. Now just for, this is going beyond that, you see there's quite a few spikes here. That's greater than 10% raw data change per pseudo plot point. So just the order of operations, let me just reset this and go to surface defaults. I'm going to go to initial settings and enable remove spikes, and then load this scaled data again. And then you see all of those spikes emanating down from the end connector. So what that's telling us, this portion of the model here is the first line, and then they picked it up and did a roll along. So either the connector at number 1 or number 56 is dirty or damaged, because this shows up once they roll. And let me go to edit, data editing statistics, and we'll see that there's 217 singular spikes. There's some data which is out of bounds beyond the repeat error. So just initially we're losing some data. This is quite normal. These command files are oversampled. So we're losing 9% right off the bat. And you'll see those spikes are gone. and we see a little bit more structure in the raw data. This is not interpretable for earth materials, but it's helpful to see the general range. These are ranges you would expect in earth materials, so that's good. But we're not going to interpret this raw data up here or the forward model. So the specifics of this project are not clear. This was troubleshooting data sent to me by the customer. So I'm just going to show you the standard operating procedure for processing these. I don't know the targets themselves here. So already we're still at a very poor misfit. Again, this RMS is not that great of a goodness of fit statistic, because if we have one data point in here which is 1,000% misfit, which is very possible, that could throw off this root mean square a lot. And just to show you what that looks like in cross plot, see here, like that data point right there is skewing our RMS greatly. So all of this inversion parameters is designed to stop before you over invert and start inverting for noise. This particular data set's very noisy. This data weight, estimated noise, has a lot to do with how smooth and how quickly it will converge. I can see right away, because of that noise likely due to the cables, getting a 3% RMS is going to be very difficult. So I actually raised the noise floor here under the resistivity inversion tab. And that greatly influences the convergence, and that's still an acceptable solution in many cases. So 10% or less. So I'm going to raise that to 10%, and I'll filter. This is the histogram removal tool, and I'm right-clicking and going to Data Misfit Histogram. And then I'm using the left and right arrow to remove 5% or less of the misfit data. There we go. And 121 data points are responsible for 100 to 200% of the misfit. So it's a relatively small amount of data of the thousands we collected here, 2439, but it's responsible for a lot of misfit. So we're going to now start the model completely over without those 121 data points. And you'll see we'll go from 50% RMS to much less than that, most likely. So just on the first iteration, we're at 50%. Now we're at 30, and so forth. So there'll be several iterations of this type of histogram data removal. I see I'm getting a couple questions here from attendees. I'll get to those here in a second. Okay, now we're at 9% RMS. So this is a usable solution. Let's look at the cross plot. Now you see it's much tighter. There's still a few misfit points. So clearly 10% is very achievable. I was a little bit overzealous with relaxing that goodness of fit statistic. So change that to 5% and just do one more histogram removal. Another thing you may want to do with this data set, it appears that in the roll along they lost depth. So these, you see that technically these are from further spaced electrodes. This is not a true depth or a true, these are different, these are apparent resistivities and pseudo plot points, but there is more data at the larger spacings over here than here. So we can trim this. And these data are generally noisier down here anyway. So this is very helpful if this is not absolutely critical, this beyond about 17 meters. And there's a nice tool built into Earth Imager for doing that as well. See, this is very clean, but this may be artifact, for example. So for this area here, let me take trim data based on depth, and I'm just mousing over this here. That's about 20 meters. See in this area here, the lower left of Earth Imager, I'm getting the X, the depth, and the resistivity of 94 ohms. So 20 meters. So I'm going to go to Tools, Trim Data based on depth, and type in 20. Okay. And now we'll have that trimmed. And if I load that, you see it's much more even. Still a little bit of let's trim that to 18. There we go. Okay, so that is a much more even depth profile. Solve that. So now we're iteration 1. The forward solution is looking more and more like the raw data. Very good. Okay. And we have more detail up here. So the model domain is smaller, and that's important. If there's a particular area in a large domain like this that's hundreds of meters long and 20 meters deep, if there's a particular target in here that you're concerned with, the best way to look at it is to take a subdomain and solve a new model, because this entire model space has to fit the smoothest solution to this forward this difference here is our RMS. So it has to search this entire model space. So you'll end up with a larger domain, a smoother solution, than a smaller domain for the same target if it's a small cohesive target like this. So that's another topic here, but we can see there's better resolution of this contact when we remove some of that depth, even out that depth, and make the model slightly smaller domain. So that's a helpful method as well. So I think I've gone over this particular data set. We rescaled the electrode spacing, we trimmed the depth, and we filtered it to a good solution. It's usable data. Initially, there were two major problems. It was incorrect electrode spacing, and there were huge spikes in that data. So okay, so there's a question here about Wenner array data. It's when using a Wenner array with the supersting, does the soil salinity need to be at a specific level for it to read the resistivity correctly? That's a pretty open-ended question. Wenner array is typically used for 1D soundings. Let me show you what I mean by that. It's the lowest resolution array for tomography for 2D and 3D. It's kind of a worst case scenario, I would say, for this type of this is dipole here. Dipole does need typically some filtering, but much higher resolution, much more detail. I could show you some examples of targets where the Wenner array completely missed them. Typically in karst, you'll miss the fractures and you only resolve the biggest ones. So that's just inherent in the geometry itself. But for 1D soundings and for grounding and lightning, like ASTM G57, it's protocol for that, and they're especially the grounding engineers, are concerned with resolving the average soil resistivity so they can design a grounding mat, the thickness of gravel, the step touch potential calculations and things of that nature. So I would say that anything from fully saturated soil with salt water up to incredibly resistive frozen soils is resolvable with the Wenner array. There's not a, if you're outside of earth materials, if you're somehow connected to metallic infrastructure, you can get errors. But that question of does it need to be a specific level, um, that shouldn't be an issue. These methods, earth resistivity and more so even than IP, which the system's capable of, has a very wide range of earth materials that it can measure. More so than say frequency domain EM. A lot of those instruments have a bounding condition. They become nonlinear at certain soil conductivities. So I wouldn't worry about um, earth materials having a soil resistivity that couldn't be resolved with the Wenner array or the dipole for that matter. So hopefully that answers that question. Okay, so we have a question about IP. I'm interested in I think that you mean exploration of copper and cobalt. I wanted to know if IP can depict the overburden and the mineralized layer. Very often, yes, IP is the go-to method for chargeable materials, sulfides. Uh, uh, there's minerals that are highly chargeable, and certainly induced polarization is a go-to method for finding those. And by proxy, the economically important minerals are resolved. So you're not imaging the gold or the silver or the copper itself. You're imaging the host material, that massive sulfide, or if it's maybe it's disseminated but concentrated enough in a vein or something chargeable. And the equivalent circuit is a capacitor, something that holds charge for some period of time and dissipates it. And in contrast to the host rock. And it can also be even diesel, for example, a spill. You can resolve the water table and diesel floating on top of it. There's a really good case I'd like you to show, or I'd like to show from Kentucky on that. And the in that case, they're using stainless steel electrodes, which are chargeable, that do increase your noise. But the target is strong enough and ground truthed, so the confidence is good there. We also have a case history on our website from the Yukon. It's pretty high profile case history where they resolved a gold deposit in permafrost. So let's go click on this. So that's the field workers. This is resistivity, and this is IP over a diorite dike or vertical volcanic intrusion, and this is that lower resistivity related to that. Their method, ground truth explorations in the Yukon, involved sampling soils for gold and other elements, and very sort of not at high resolution, but reconnaissance. And then when they would have a spike, they would go in with more invasive methods, geophysics and drilling, and the soils don't move very much from the source material in this particular part of the Yukon. So that chain of events was economic for exploration, and they weren't sure where the dike was. They knew it was nearby, and the resistivity finds that. The IP, interestingly, is not directly over the dike so strongly, but offset. And this can be for two reasons. It's not clear just from one 2D line, because there's a 3D component here we're not accounting for. They had time to set up just one line. These are two models from that one line, and they captured that dike, and they also drilled into it. Let me show you the drill data. That may not be in here. Ah, there it is. Perfect. Okay, so these lines here with histograms are the coring data. The histograms are the gold tonnages, 3 grams per ton cap. So that is highly profitable. That is definitely that's being mined for sure. And you can see that the highest histograms are near the dike, and they actually go below the exploration depth. They didn't have long enough cables in this case. But again, this is difficult conditions, and they used stainless steel stakes, but with good results. And that does greatly increase your efficiency in the field, because you don't have to put out a non-polarizing electrode for the receiver. This is transmitting and receiving on stainless steel, which in many cases is possible. So for gold, silver, copper, I would recommend this, as long as you have the exploration depth needed. If it's a much deeper target, you would need longer lines, more electrodes, and possibly an external transmitter, which would be our power sting. In this case, for the upper couple hundred meters, they were doing fine with the super sting. Very sensitive receiver. So hopefully that answers that question there about copper. There's a question here. See some familiar names. Would you trim first, then see what happens? I would solve the full domain, the full model set, so that, because you collected those depths, if there's a target of interest in that, then do a subdomain. Work down from the largest set. That's in some cases there's like a DOT, a Department of Transportation, may be only interested in the upper 10 meters or so. Perhaps you collected that full depth, and that's a good question. There are ways of saving time in the field. I'm going to go to our SS admin program. This is the PC version of our app. I'm going to make a dipole command file. The red and the blue electrodes are the transmitters and receivers. Do that again. And the green the red and blue are the transmitters, the green are the receivers. These blue and red points are the near surface. This particular one takes 26 minutes because it's an R8. If you had the lower cost R1, it would be 2 hours, and you see it's doing each reading in singular fashion, one channel. So that's the benefit of having a multi-channel instrument. The R4 is the probably the most efficient cost versus speed, but still for consulting, the R8 is the go-to, because time really is critical. It's 40 minutes with an R4. Reasonable, but not what you would want. You would want twice as much data per day, typically for consulting. But you can always upgrade later from the field side. So if you wanted to speed this up, let's say you did have a R8 and it was taking 22 minutes or 26 minutes, sorry, and you're doing a DOT project, perhaps with roll along, we can turn off. Now we don't want to turn off receivers. We turn off transmitters by reducing to 3 A spacings. Okay, So that's going to be the blue, the red, and this light blue here. Now notice the timing here. None of this is saved in the command file. This timing estimate is purely for project management, because what I mean by that is you can use the same command file for all of these measurement times and cycle times that is set up on the SuperSting. And then of course the scaling, which we talked about earlier, the electrode spacing is set up on the SuperSting as well. So for dipole for 56, if that's your switchbox size or dual mode size, then that's the only command file you need. This is the name that would show up on the SuperSting. And then create reverse array is a little bit more efficient if you go with roll along, same as a forward array. I wouldn't use extended coverage. I would go into that. I'll go into that later. That takes up a lot of time and is some fractional dipole spacings, marginal increase in resolution, but really a time hog. For that amount of time, for maybe 5 minutes more, I would collect another array, the inverse Schlumberger as a backup, or the strong gradient, which we can do in Earth Imager. But this is really the go-to, the dipole. Now here, notice it only takes 20 minutes. So I cut 6 minutes off, and we're not getting this deeper data. So that's a quick way of collecting the near surface data is always stronger. And if you're doing a DOT project, this is a way of doing it a little quicker and just the strongest data. But really it's 26 versus 20. So that extra 6 minutes, if you're going to go to the trouble of putting the cable out, I would suggest collecting this as well and maybe trimming that off if you need to. So hopefully that answers that question. Can the depth scale be set to even increments? Okay, it can, but it shouldn't. That's a good question. The depth scale. Now, notice that, okay, these electrodes up here, they're at the surface, and these are pseudo plot points. They are not actual sampling locations. This is just a convenient way of looking at raw data. And it telescopes down so that the instrument collects a reasonable resolution at depth. You don't want to sample at high resolution at depth because these data are smoother anyway. The mesh should expand. Let me show you that in Earth Imager. This is that data we were working with earlier. So I'm going to reset Earth Imager, go to File, Reset Earth Imager, go to Surface, Tools, and I'm going to create this. I can do the dipole. I'm going to turn off signal strength. That is often you really don't know what the average apparent resistivity is and the injected current ahead of time. And this is the signal strength check would be a way of parsing out data and having it run a little faster. I would generally not have that selected because these are almost never known unless you're doing the time lapse, reoccupying the same site. So I'm going to create this dipole. I have to create the geometry first. I'm going to default to 1 meter so we can use that scaling factor on the SuperSting. So again, this 56 electrodes would be the only command file needed. We can even put an end address of less than 56. Otherwise, you leave that blank. That's a setting on the SuperSting menu. So I just went to Surface tab, Settings. Then I'm going to create that command file. And under Simulation, notice this is a higher level dipole. This transmitter position is narrow here. The closest receiving dipoles are narrow and they telescope outwards. See, this one's wider. So it's the same dipole that's collected and generated by the SSAdmin or the app, but the dipoles are telescoping. So what that does is for this narrow spacing, you collect the higher signal, your source is here, and this is the weakest. Voltage falls off with distance from the transmitter. So a wider dipole spacing will give you larger potential. So that's going to increase our signal to noise. So it's collecting it in a higher signal way. And you can see that it steps like that with telescoping dipoles. So let me save this. I'll just call it temp command, or no, we have 8 characters that would show up on the supersting. So DD56E for Earth EI, Earth Imager. Okay. Now, if data was collected with that, we would have an STG file. I can load that command file it's going to ask what spacing there. So this is the mesh that, and this is answering that question: can depths be set to even increments? It can, but it shouldn't. This is telescoping down to account for the loss of resolution at depth. So that leads into another question. If you're designing your exploration depth, which is a function of the length of the line, you should have your target in the upper half of the model section, because down here you see how coarse the mesh is, and that's a function with any surface geophysical method where your sensor's at the surface. You always lose resolution with depth. So this is not where you want your target. So you would need a longer line and more electrodes. And you see the resolution is much finer up here. It's half the electrode spacing, but it falls off with depth. So that's why the depths telescope down like that. That's actually correct, and you really want to do that. If you were to do something like this, that would be a higher chance of artifacts down here. You're solving all of these finite element cells at a resolution that's not appropriate, and the only time that this would be appropriate is if you actually had a borehole, and an Earth Imager would automatically account for that, and that would be, let me show you. I'm going to reset Earth Imager. And again, surface defaults is the way to go. This is the correct mesh, and hence the depths will be telescoping for a surface electrode array. So that's correct for a surface electrode array. If it was a cross borehole array, I have a command. I can generate one actually. But it'd be easier just to, that's under the command file creator. I'll just load one from our demo. We have a lot of stuff in our demo folder. And that's under C drive. And this is with all Earth Imager installations. Demo. Just gonna look for the borehole. Cross borehole. That must be it. Okay, there. Now you see this, there's a surface array and then 3 borehole arrays, and the mesh is even because there is no loss of resolution with depth in this case. So this is a very constricted site. You can see it's only 8 meters here and 10 meters down, but the resolution down here is almost the same as up. There's a few more electrodes. There's these surface electrodes, so slightly better at the surface, but very good resolution down here as well. And that's where you would have an even depth scale. Okay, so that's that question there. Question about reverse mode more efficient than forward when rolling. Okay, so roll along. Oh, this is okay. So the motion of roll along is in the forward direction. There's a confusion here on what reverse and forward means. Reverse means that the command file itself collects in reverse, but you are rolling forward. So that's what that's this one happens to parse more efficiently in the overlaps. So you don't collect redundant data. So if you're doing roll along, you use create reverse array. That just means that it collects like this. It doesn't mean that you roll in the reverse direction. You're always rolling forward. So your switch box is here. You pick this cable up and you move it this direction. But the command file itself is on each position is collecting reverse. And that just parses slightly faster when it's not, this little portion of the array is not repeated on roll. So roll along is more efficient than picking up the entire cable. I'm doing like slide along. So got that question answered. Why are there many low and high vertical lines in a limestone bedrock contact? That is a question that came up, and it had been nagging a customer working in karst areas. And I was able to reproduce the artifacts here with the same data and then make them go away simply by changing the start model. And they had used pseudo section start model, which is inappropriate for anything but a homogeneous case or a nearly perfect, almost homogeneous layer earth case. Like in some marine settings where you have a water layer, that water layer is homogeneous and that's the bulk of the model, and you just want to solve that sediment water interface, something like that. You might get better ground truth correlation with a pseudo section starting model, but it is not the default in Earth Imager. If you change to a pseudo section starting model, it'll greatly change the end. Changing your starting model highly influences the final result. It's a bit dangerous. So let me show you what I mean here. This is a karst. Now I had to. This is a real project that they were. I mean, everything's a real project, but this is a commercial. A bit sensitive because sinkholes and karst, and so the property and the data and the area, everything's sort of hidden here. I was just helping them QC. So, but I can tell you that there was a feature that they were worried about at this construction site, and they imaged it and they decided to move the building, the foundation, away from it. And that's something you'll hear quite a lot, where a sinkhole opens up in a parking lot near a large building. And what I always think when I hear that is, well, that's good. They may have known that there was higher sinkhole potential there, so that's why the parking lot was put there. Because it's much more acceptable to have cracks and foundation issues in asphalt parking lot than in the slab of the building and such. So here's their data sets. They weren't able to go exactly over the karst feature of interest. Probably there was some cave-in or something blocking it, but they did image the edges of it, and they do correctly block out the base of it, because their pseudo, their lines were not fully overlapped. And what I mean by that is, if they wanted to fully resolve this part, it's done with two models here, and you can see they're only overlapping maybe not even 25%. It would be better for these to overlap at 50%, and then they wouldn't have this no data area here. But yeah, this is where they wanted to put the building away from that feature there. This is a depth to bedrock contact. See high resistivity. Now, these edits that I'm going to talk about don't change the interpretation here, but they get rid of this. This is artifact. You see those spikes there? They were very concerned about this, but they were not able to troubleshoot it. And let me zoom in a bit here. So the depth of bedrock is the same. You notice these models are much smoother. They all have good RMS. okay? But RMS is not the end all be all of a good data set. You can solve a low RMS for a data set with a lot of artifacts, unfortunately. And the phrase there is multiple non-unique solutions. It sounds scary, but these modeling methods are somewhat ill-constrained. So you have to be really careful with your starting model and look at the data before you solve the model. Look at the raw data for any spikes, any clear metallic infrastructure interference, and I'll talk about that. So what happened here is, and I looked at the INI file here. You can load it in Earth Imager, or you can load it in TextPad Viewer. And what I saw was that the starting model was not the average apparent resistivity. It was changed to pseudo-section. So if you have surface defaults in Earth Imager, I'll show you that. Let me reset this. If you have surface defaults, I'm going to click on this icon here. We have the telescoping mesh that we talked about earlier. We have these are good boundaries for typical Earth materials for the raw data. And then the resistivity inversion, we're estimated noise of 3%. That would be nice, clean data. Sometimes you can't achieve that. You need to raise that estimated noise. Here is what was causing all of their issues. Occasionally, somehow, they were resetting this, or this was set to pseudo-section. Perhaps from another user. Like if I say OK here and I close Earth Imager and then I open it again, see it says previous settings. It's using whatever settings the last user used for Earth Imager. So it's critical that you reset this to surface at all times before you run a model. Now let me show you what happens here. Now this is excellent data. It's clean data. I'm going to go here and load the west side. I'm going to use normal surface defaults. And this is we're not interpreting this, but we're seeing the general range. That is generally the bedrock, and that is the soils and air surface. But this is what we're going to interpret here. And then this is the actual karst feature off to the edge. So notice that this bedrock contact is much smoother. There is some kind of potentially a joint in the limestone. From just one 2D line, it's hard to tell, but there is a lot of data that is resolving that slightly lower resistivity. And in limestones, that could be a vertical joint. But this is really what they're concerned about here. I'm turning off the blanking. The default aspect ratio is 1 because we don't have additional electrodes over here. So you always want to show it that way. But notice the RMS is 2.72, very tight fit. That's excellent data. They had low contact resistance. If we go to injected current, so I'm going to edit, debug surface raw data, injected current. Beautiful. They got 242 milliamps up to 500 milliamps. So if they wanted to collect IP, they would have gotten good IP here also. The measured voltages were all very high. The supersting is stable down to tenths and hundredths of millivolts. Like in marine projects, you often have very, very low millivolts. Here it's up to 1,000 millivolts and 3 to 1,000, very, very strong. And then the repeat error here also way less than 2% standard deviation, very clean. So this is all very good. Now, if we go back to this PDF, what they were concerned about was this. So I noticed that in some of their INI files, they had a different starting model, and I wanted to see if I could recreate that. So I just went to here, changed that to pseudo section, and then ran the same data, and we'll see those artifacts now. It's taking this pseudo section and imposing that structure, which is not real. That is not a real structure. It's apparent resistivities and pseudo plot points. It's taking that structure and starting the model from there, and then fitting a smooth solution. So in order to do that, because it's ill-fitting from the start, you end up with these high, low, high. This is typical of instability. It's basically instability in the convergence, and it still has a low RMS. And the depth to bedrock is approximately the same. It doesn't impact the project, I would say, but it is it that joint which is there in the apparent resistivity starting model, final model, is obscured by this. So again, using this pseudo section as a starting model is not appropriate for complex, typical geology. It's an option for here. That's what you want. And further, you could even put a custom one in, but this is very risky. The most defensible way to start these is average apparent resistivity and surface. And if you have any questions here, feel free to email me further, or send me a data set you have questions on. That's how this was solved. They sent me the data. I quickly found out why that was happening, and we solved it. So if you were to look at this in a text viewer, the pseudo section starting model would have a res start ID equal to 0. The one you want here is res start ID equal to 1. So you could do some forensics later if someone was to give you the INI file. So you can figure out what they used to solve that model. And why. So the other ones were smooth. It's just something happened in Earth Imager that reset. Someone else used it, or it must have been that. So the moral of that one is to set surface defaults each time, which would be just like this. Okay. There's a question here about an older firmware, which would tell the operators when a particular model or when a particular cable section was done. That's been removed in the firmware because it only works on a very specific type of command file. And that would be a forward dipole made in SSAdmin. And if you made it in Earth Imager with that telescoping array, or if you had a merged command file like dipole strong gradient or dipole gradient, some of these higher level command files, that signaling. So basically, it was signaling the operators to pick up a cable section while the supersting is still measuring, and that was deemed too much of a risk, because you could go to the wrong part of the cable, or you could be running a command file that wasn't compatible, that may cycle back, and it was too complex and too risky of a solution to make things more efficient. So the only way that you could use that is to use that old firmware, and I wouldn't suggest that. So that's a roll long function in the very early days of the roll menus in the supersting, and we had to remove that for safety reasons, and because of these higher level arrays becoming more popular. So hopefully that answers that question. I typically use a deep cycle marine battery with Supersting R8. Is it always better to use a booster battery, or all dependent on environment, sandy versus clay? Okay. This is this question about main and boost batteries. And that's, I believe I've got that added to our website. in the help desk area, and then I'll go here. And I added the critical contact resistance. Boost. Okay, so main and boost batteries, or main and boost power supplies. This is really the best option, a small Honda generator. This generator here is about $700. You can rent them at Home Depot. It doesn't have to be a Honda, but that's a good model. That little tank of gas is 1.5 liters or so, would run more than 8 hours constantly on this. That's the main and that's the boost, or vice versa. Each one of these takes the place of a battery. That's 27 pounds, and these are a few pounds more. Each one of these can be 50 to 70 pounds. So you can see that this is a much lighter solution if you're moving around a field site, and you don't have to charge. These have to be charged overnight. And these need to be 50 milliamp or higher to be stable, because the Super Sting can cycle between a 2-watt load up to a 900-watt load. And that's this Honda 1000 IU is a 900-watt RMS generator. That's you could use a Generac, you could use other brands, no problem, as long as they're 900-watt. This boost battery is there if the contact resistance is less than 1800 ohms. Okay, and that's Ohm's law, controlling the impedance, or how much current we can get into the ground. And 200 watts is boost mode, 100 watts is main. So I would say it is always better to have boost if you foresee having good contact resistance. If it's extremely poor contact resistance, there's no point in connecting the boost battery. So if you know contact resistance ahead of time, you could plan to take the main or the boost. That is something you may know if you're reoccupying a site. So the contact resistance controls whether the boost is actually used. The boost light will come on the faceplate of the Super Sting. I don't have a picture of that here, but there's a main and a boost light next to the power switch on the Super Sting. Let's see. Of course, never connect to a battery in a vehicle. This is may not damage the Super Sting right away, but it stresses it because the alternator is cycling on and off, and that spikes the battery. In cars, the electronics are shielded from that. The Super Sting cannot be shielded because it is, in a sense, measuring a ground loop all times. The receivers have to be open, and they are very highly sensitive. And the reference for those measurements is a floating ground, which is assumed to be isolated. And this, when it's in the vehicle, it's not isolated. So you want nothing else connected. In a pinch, you could use this battery, but you need to disconnect it from the vehicle. And of course, you don't want to run it down to the point where you can't start the vehicle. Speaking of ground loops, this is the best way to place a battery on a piece of wood or a rubber mat, because it is possible that there could be some slight electrical leakage from the post to the earth, and that would contaminate these data there. And then the other thing to watch out for is, main and boost is 2 sets of battery clips that go to 1 mil-spec connector that goes to the Super Sting. If you were to connect both to the same battery, that would be a shorted condition, and you would see that right away. That would be a problem. Okay, let me see. I think what type of array? That's a one-line question. What type of array? Well, I would recommend for 9 times out of 10 for geotech, near surface environmental projects, dipole. And there's a way we made that. Do you remember we made that dipole 56, you can make a merged command file. At the end of the dipole-dipole, you could tack on strong gradient. Very quick, high signal strength array. If you remember that data set initially that I rescaled, this one, remember how there's some missing data here? That probably is missing because the deeper data was too noisy. If he had a merged array command file, he may have been able to collect that data. And that, let me show you how that's done. Now command file creator, surface, we add 56 electrodes at 1 meter. Then we made dipole. I would not suggest this dipole edge gradient. That's this combined one. That uses the first and last electrode a lot, and if you have contact resistance issues there, it can be a problem. What I would suggest is making this dipole, turning off signal strength, create it, save it. We already did this here. We called it DD56EI. Now go to strong gradient here. Turn that off. 50% overlap's fine. Create. Now this, notice that strong gradient is an 8-channel reading on every single measurement, and it's a nested array. The transmitters are on the outside, receivers are on the inside. This is a lower resolution array because we're not sampling the potential field as accurately as in dipole-dipole, that by removing the receivers to the outside of the transmitter dipole and sampling that gradient more accurately. But we are sampling it in the very highest signal portion in between the transmitter and receiver, and in full 8-channel mode. These electrodes here that I'm pointing to are actually Wenner. And then this would be something close to Schlumberger. And then out here is gradient. So you can see in 8 channels, we're getting basically Schlumberger, Wenner, and gradient all together. So it's very efficient, quick, low resolution, but high signal. So this can help fill in gaps if your dipole is missing it. And notice that it's 4 minutes. It's almost not even a question of that if it's worth the time for a 22 or 26 minute array. So if I save this one, I'll call this SG56. And it's right next to the dipole 56. And then close. And if you make your command files in Earth Imager, it's very easy to merge them. Merge command files, add. I'll run the dipole first, so I load that one first, and then I'll add strong gradient, open that, and then merge. And I'll call this one DD underscore SG56. So that's dipole strong gradient 56. And that is the array I would recommend for any 2D 56 surface survey. That will help a lot. Okay, so that should answer that question. What if commands are created in an AGI simulator? Commands are not created in the simulator. There is no, that simulator is purely, okay. That question we did answer earlier. Let me show you again. Okay, so the simulator, the simulation tab, none of this is saved in the command file. This is a simulation of time. So in that strong gradient that we just made and saved, if we change any of this, notice, let me go back to surface tab. Okay, I have to reset Earth Imager. Add surface electrodes. Let's say we had dipole-dipole and create. So the question was, what if we make command files in the simulation tab? You're not making a command file in the simulation tab. This tab is there to give you an estimate of time. So if you save this command file, upload it to the SuperSting, and you happen to run the SuperSting at 1.2 second measure time, it would take 42 minutes, 37 seconds. If on the SuperSting you changed it to 800 milliseconds, it would run in 38 minutes, 59 seconds. So if you turned on IP, it would take an hour and 8 minutes. This is a time estimate, survey time estimate. So hopefully that's clear that this is not saved inside the command file. This is for project estimates. Surface, settings, geometry, all of that is what's actually written inside the command file. So you only need one command file. Again, these are set in measure settings, menu 6.1 on the SuperSting. Is it wise or not to use extra remote third, fourth batteries near both ends of cable layout? Okay, I demonstrated the dipole-dipole just now. Got that done. Oh, what type of array was used on the Karst project? That was a dipole-dipole strong gradient. Is it wise or not to use extra remote third and fourth batteries near both ends of cable layout? Okay, so this customer must be talking about dual mode electrodes that are very long. So if you have dual mode electrodes, this is a special case. It doesn't, switch boxes don't use these extra batteries or amplifiers. Let me just talk about this really quick. So under products, we have these dual mode dual mode electrodes. It's under accessories. There we go, active electrode. Okay, so the switching electronics are inside here. You can have hundreds of dual mode electrodes out, but only have a few wires inside here because there's a dedicated transmitter and dedicated receivers and a comm line and a power line and things like that. So these have to be powered and communicate. If you have 180 or 200 of these, periodically you'll need a little amplifier that boosts the communication signal and the power. It does nothing for the transmitter or receiver. It's not a booster for the 200 watt transmitter on the SuperSting. It's merely to help communication for very long lines between those electrodes. So if you do a relay test before you run a dual mode survey, you'll know if everything's talking to the SuperSting and if you need to move your amplifiers or even add them. So that question about is it wise to put batteries at the end of the line, I think that must be related to these, because other than that, putting, as far as a switch box system, it doesn't matter where you put your batteries as long as they're not coupled to earth. They should be up on wood or plastic or some type of insulator. There's some cases where you only use half your passive electrodes, like if you have a switch box 56 and you want to run 28, you can put the low address port on the switch box at either end of that cable. It doesn't matter. There are some cases where a connector is damaged and you may want to move to the other end of the cable to avoid that particular connector. But those are all troubleshooting issues, site-specific troubleshooting issues. So, oh, okay. Can you show the combined strong gradient dipole-dipole simulation? Sure. That would be our, that looks like our last question of the day. We're running a bit late. Thanks for bearing with me here. Let me show that simulation. So that merged command file that we just created, I'm going to load command file. So the DDSG56, oops, yeah, that one, that has to do with the merge header, but it is not an issue. You won't see an error on the SuperSting. So this little simulation tab, when it initially loads a merged file, it sees a conflict, but you're not going to have an issue on the SuperSting. So we have that in the bug fixes for this visualization. So this is purely a visualization tool. It's not used for modeling or anything like that. So it's doing the dipole right now, and it's running through the command lines. You can see that there's 1,542 data points in 43 minutes. I have it here set to a simulation speed of 500 milliseconds. It's kind of slow, but it's letting you see all of those telescoping dipoles, and eventually at the end it'll do very quickly the strong gradient. And I think, yeah, let me speed that up. Run this quicker. There we go. And there's rules to these dipole. For example, n greater than 8 isn't collected, because typically those are, here's the strong gradient, those are weaker. That's why the SuperSting's an 8-channel instrument. And then that's this strong gradient. So yeah, thank you all for attending. This webinar will be put into chapters, and everyone registered here will get a link to download later when it's been cleaned up. Thank you all for the questions, and feel free to contact me anytime. And we'll see you next time. Thanks. Bye.